Okay, let's start with our first example. All right, the first example for small sample. First example for small sample hypothesis testing here. The hormone levels of 6 patients are measured. Hormone levels of 6 patients are measured, which has an average arithmetic mean of this much, and the standard deviation of those numbers is this much. Oops, this 10 was extra here. Okay, that's your standard deviation. Now, we know that from previous scientific studies, we know that that value is 0.500 in normal people, or normal people who are not sick with a particular disease, for example. So for that particular disease, does this mean this increased hormone level addresses those sick people? So are those hormone levels, let me write the question here, are those hormone levels are increased with respect to normal people, of course, in that particular disease people, in the patients, okay? In those patients, is it elevated or not? That's what we're trying to figure out. And it means that your alpha should be decided first. Let's suppose that it is, we want to speak with, or we want to make an inference with 95% confidence. Okay, so what would be your H0 hypothesis here? Your default should be the same. Okay, so your mu is 0.5 is the default value, and your alternative hypothesis is your mu is, be careful, we're wondering if they're increased in the sick people. It's not two-sided, right? It's one-sided and on the right-hand side, so it means that it's larger than. This is what you will be testing here. So when I try to find this, your t value here, now I can use S, your standard deviation from samples, comfortably. That's it. S over this one. We have all the values here, don't worry. 3 minus 0.5 and point. This is also given to us, our standard deviation over square root of our sample size, which will result in a t of what? 131. This is where I'm located. Okay, this is where I'm located here. It is, and suppose that it is 131 is something here. Okay, but what I'm curious about is for alpha equals 0.05, what is my critical value here, or here, for rejection region here? This is what I'm wondering here. So it means that the remaining part will be, I mean, not the remaining part, of course. It's we can use the table directly here. But what you have to keep in mind here is that it is one-tailed. So you put this directly and calculate for this. And how many did you have here? Do you remember? 6, right? So your n minus 1 is 6 minus 1 is, your degree of freedom should be 5, right? And in that row, your tail probability is 0.05, and the corresponding value here should be 2.015. So hey, that's it. That's what we have here. If we're on the right hand side, we will reject 𝐻0. If we're on the left hand side after the transformation, we cannot reject 𝐻0. That's it. Now let's put it and try to make a conclusion. Where is your rejection here? Right here, right? It is 2.015. This is your rejection region. And no, you couldn't reach it, right? Now the answer to this question is 𝐻0 cannot be rejected. That's it. That would be your answer, nothing else. 𝐻0 cannot be rejected. If you want, put a sentence to it as well as a cream, like hormone levels are not elevated in patients with that particular disease. That hormone levels are not elevated in patients with that particular disease. Okay, that's what we're finding here, and your confidence region was for that. Particular example, your confidence region was before, your confidence region, like your x plus minus z alpha over 2. This is for before. If you want to find this out again, so this is for the large sample analysis here. This was for, but here, for small sample, here we write x plus minus t alpha over 2 with the degree of freedom. You find this critical value here as x, where your Sx equals s over square root of n, right? So, oops, this is what we're doing. This is what we're doing. And for alpha equals 0.5, your region should be 0.25 to 0.25, separated like this. And what would be those corresponding threshold values here, plus minus? You take this out for 0.25 here, for the degree of freedom of 5 again. Go ahead and find the value. You're trying to find the upper and lower limits of this increased hormone levels, right? So it would be, your critical value should be 2.571, and instead that should be 2.571. All right, 2.571. So when you do this, oops, like what is going on here? What is this? 2.5 plus minus 2.571, your standard deviation over square root of your samples. And if you use your calculator, you're gonna end up with plus minus these upper limits. Okay, something like this. So in the end, your lower limit and your upper limit can be identified here as 471, and your upper limit is 589. So it means that since your 0.5 is somewhere between here, you cannot reject your, with 95% confidence, your mu lays between this range. That's it. And you cannot reject your null hypothesis here because it's laying in the middle. That's the idea. If you want to narrow the confidence interval here, what you have to do, Just pause the video and think about it. You already know this, and it's just so if you want to narrow the confidence interval here, you need to raise your number of samples, right? The more samples you have, you just narrow your confidence interval here, and your degree of freedom will increase, and your standard deviation will also decrease here. That's what we can say about this small sample hypothesis testing example. All right. Okay, let's go ahead and solve the next example from our textbook, namely the second example. 10 cherry plants are checked for whether their average weight of production is 205 grams. Okay, this is it around this or it's different? That's what we're checking. And the data is given to you like this. When you measure their weights, we will end up with these weights. I'm writing them one by one here. 4, 216, 318, 190, 181, and 225. All right. So go back to chapter 1. Remember what we're doing it. I mean, it's easy to find their arithmetic mean, right? You can also use some, web-based calculators or something for finding the arithmetic mean here. So it should be 2, 2, 3, 1 over, you have 10 samples here, and your arithmetic mean should be this value. Okay, when you make the necessary calculations, you will get a square root of difference from the mean, and when you divide them by the sample, okay, size, which is n minus 1, and you will end up with this value hopefully, and your S will be 441. Those could be given to you directly, or you can directly calculate them from data, from your experience from chapter 1. That's okay. So now we also need our type 1 error probability here, which is your confidence level, and it is set as this value within this question. So build your null hypothesis first, which is your mu equals 205. Your alternative hypothesis is mu is not equal to 205. That's it. So I need to have my rejection region here, but be careful, since it's not equal to, it means that that would be two-tailed, and this need to be divided by 0.5, right? So what are those threshold values here for n equals 10, right? This is what I'm trying to figure out. Oh, I go back to here and I will find that lovely value here, this one, and my degree of freedom is n minus 1. I had 10 samples, right? So my degree of freedom is 9. I look at the corresponding values. Okay, I found you. 3.25 is my critical values here. 3.25. This is for plus and minus 3.25 right here. Okay, good. So your T is, when you calculate this, 231 minus, this is what we're testing against. See, your average arithmetic mean is right here. 40.41 over square root of 10, s over square root of 10, it will give you 1.416. So where is it located? 1.416. It's located right here. Can you reject H0 here? Are you laying right here? No, no. So your answer should be H0 cannot be rejected, and that's your answer, and that's enough. So they're not different. I mean, their weights are not different from, in other words, 205 grams. And so if you want to calculate 95% confidence interval for production as extra, it means that your x plus minus t with the degree of freedom 25 and 9 here. Why? Because this results in alpha being 0.5, and since it is confidence interval 0.05 to 0.25, that's why we put this. I mean, maybe you're getting used to it already. 0.025 here times Sx. So that should be, but you need to look it up, right, for this value. And what should it be? 0.02549. 0.02549. 0.25 for degree of freedom 49. It should be 2.262. 2.262, right? Yes. Let's put it here. So this value should be 2.262. The other numbers, or the other calculations, the other data, we already have them. Your Sx equals is s over square root of n, which is 4.41 over square root of 10, which is 12.779. This is your x right here, and your x is already given, 21 plus minus. When you make this necessary multiplication here, you will end up with hopefully 28.9. Please use your calculator as well, and then you can have your lower limit and upper limit here comfortably. Your lower limit should be 194.2 grams, and your upper limit will be 252.0 grams. So what does this mean? What does this upper range and lower upper limit and lower limit tells us? This range covers mu, also known as the population mean, the mu. This range covers mu with 95% probability. With 95% probability of these samples as taken, their mu, this population mu, will fall within this range. Okay, this is what we understand from this 95% confidence interval right here. Okay, we had solved an example about bird weights difference with large sample hypothesis testing. Now we will solve the same similar question with small sample this time and try to figure out whether their weights are the same or not. So this would be this third example from our textbook, and we're wondering whether bird weights are same or not. Again, we're curious about this for alpha equals 0.05. Okay, this is what we're curious about. And for males and females, again, we make some measurements, and this time their n is 9 and 10 here, and 10 and 9 here. So as you see, this small sample, right? Before it was 100, like 85 birds and 120 something birds, right? So we were able to do a large sample hypothesis testing. But when we have fewer than 30 samples here, we're going to go ahead and do small sample hypothesis testing here, and their mean is here 90.8 and 81.52, and their variance is given as 55.2 and 66.2. All the data are given to us. We have everything. We have our rejection region, rejection value here. Let's calculate all of them. But the only thing that will be introduced to you here is how we calculate the combined S square here. Like this one should be, okay, if you want to memorize, go ahead and memorize. I won't say anything to you again. We don't go into detail of proofs here, but that's the idea. That's what is written in the text here. For small sample, this combined S square is calculated like this. Combined variance is calculated like this. You see, you subtract 1 from those sample sizes, and your S square would be 9 times 55.2 plus 8 times 66.2 over 10 plus 9 plus minus 10 plus 9 minus 2, and the result will be 1026 over 17. Please, you make the calculations yourself as well and tell me if something is wrong. It would be a nice practice for you as well. And this is your S square. So great. Now let's try to figure out and find out our H0 and H1 hypothesis here. H0 is mu1 minus mu2 equals 0. H1 is mu1 minus mu2 is not equal to 0. All right, this is how we build our null and alternative hypothesis here. And your t here should be x1 minus x2 minus 0 here, s x1 minus x2. So that should be t equals 90.8 minus 81.52. You have them over 3 point. But we hold on. How we get s x1 x2 here? Do you remember from the when you have this combined, n1 plus n2, the combined standard deviation here will result in something like this. It's 60.28, 1 over 10 plus 1 over 9, and that should be the square root of 12,747, and that should be 3.57. Okay, this is what we're curious about. Here is the combined standard deviation here, so that's one, and the result will give you 2.6. Okay, but where are we? What is our rejection region here for this value? It means that since it is not equal case, I understand that that should be two-tailed, right? Two-tailed. And what should be your degree of freedom here for combined? Remember, 10 plus 9 minus 2 here. So that should be 17. For degree of freedom of 17, we will look this point 0.25 value here from table. Okay, for this value, okay, for this value, and degree of freedom of 17. I look it up, and it is 2.11. All right, it's 2.11. That's my critical value here, which is 2.11. So I put this value here as two-sided. That's 0 and 2.11 here minus 2.11 here. And where is your t transform? T is located here. It is located at 2.6, right? So it is in the rejection region, so it is rejected. 𝐻0 is rejected. That's your answer, and that's enough. 𝐻0 is rejected. So what does this mean as a sentence? Those male and female bird weights are different. They're not the same. Okay, this is how we conclude this. And for 95 confidence interval here, for mu1 minus mu2 here, you just set your upper and lower limits here. Oops, upper and lower limits of difference as 2.11 times your standard deviation, right? This value is your standard deviation, and that should be 9 plus 7.53, and your lower limit for difference, lower limit for and upper limit for weight difference should be 175 grams and 1681 grams. 95% of measurements of difference will fall within this range. That's what we're expecting, and since zero is not here within that range, we can also conclude that their weights are different. Plus, the bonus conclusion is male birds are again a bit heavier, because you're finding yourself on the right hand side as well. But of course, this is a bonus conclusion. Okay, this was all about the small sample hypothesis testing as well. Don't forget to solve many examples in your own to practice. Okay, thank you for listening.